giving me an opportunity to speak here. And basically, this will be the condensed talk of what I gave last week here. Anyway. So today I'm going to talk about algebraic Montgomery-Young problem, which is still open. And I want to propose cascade conjecture. And I want to claim that this conjecture implies the original problem. And this is algebraic because the original problem is Montgomery-Young problem, which is problem in differential topology. So today I want to talk about the Montgomery-Young problem first, and then algebraic version, and then I will propose my conjecture. Okay, so let me first start with this conjecture. So algebraic Montgomery-Young, it is proposed by Tolar 2008. And the statement is like this: that S be a normal projective surface with quotient singularities. And if the second Betti number of S, the topological second Betti number of S is 1, and the smooth locus of S is simply connected, and the number of singular points is bounded by 3. So this is the conjecture. So probably at this moment, most of you already got lost your interests, because maybe you did not find any motivation to study this problem. So I really need to explain what Montgomery-Young problem is, which is the motivation behind this conjecture. Okay, so basically this is a problem about self-corrections on some odd-dimensional manifold. So let me start with that action. So I'm going to introduce what is called the pseudo-free circle actions. So probably you don't know what this is, so let me define what it is. Here smooth means C infinity. Smooth circle action on a spot Sn, the sphere, is called pseudo-free Okay. Can you hear me? Okay, so if this action is fixed point free, but we want this not free, and but still free except possibly for finitely many non-free orbits. Okay, so this might be complicated, but I will give you an example soon. So before that, I want to remark several things. So first, in this case, the dimensions should be odd. This is by left-shift fixed point, because for example, for non-example, if you consider standard circle corrections on S2, like acting like this way, then you can easily find two fixed points at the North Pole and South Pole. So there are two fixed points. So in the even dimensional case, you always have two fixed points, and in odd dimensional case, you don't have fixed points. So because this is not free, the dimension should be odd. Okay. And the isotopy types should be cyclic groups, like this, where those numbers are relatively prime. Okay, so this is kind of standard. Okay, let me give you an example because this is not algebraic geometric, but still there is a connection. So I want to introduce this example. So it's a diagonal action. So most simplest kind of examples such. So consider the standard embedding of the spheres. And circle into complex numbers. So I assume that these are unit spheres with standard coordinates. Okay, so you can embed like this. And let me explicitly define the action. So the circle acts on this r-dimensional sphere this way. So we can use this standard coordinate now. And it diagonally acts like this. So it is one of the most natural things to consider. Here, the powers are relatively prime. Then this is the pseudo-free subcorrection actually. And it has at most n non-free orbits, and the non-free orbits are occurring in those vertices. So the picture is like this. We have this. This doesn't look like r-dimensional sphere, but let me draw it this way. And we consider the orbit space by this subcorrection. Then at those coordinates, you have these points. And at the general point, the inverse image, the fiber is just a usual circle. But over these vertices, you have circle wrapped around several times. And the order is exactly those numbers. Circle is wrapping A1 times and here AN times. So this is basically the picture. What is happening here? Sorry? Yeah, pairwise co-prime. Yeah. So this is essential. And this orbit space is, in this case, isomorphic to usual weighted projective space. So this is the object that we are familiar with. So actually, so this is called what is called Seifert fiber bundle, and Seifert first introduced this notion for S3 in his study of three manifolds. It appeared in the first talk in the morning, and then Oleg and Bagras generalized this notion to any higher dimensional cases, and then Kolar studied this vibration structure because there is a famous Kell-Einstein, Sasaki-Einstein correspondence. So roughly speaking, if you have a Kell-Einstein metric here, then you have Sasaki-Einstein metric here, and vice versa. And this was motivated by ADS-CF correspondence related to here, but this is Kolar's motivation. And we are not considering this thing today. Anyway, this is a well-studied subject. And so, as you see here, from this highly non-algebraic geometric object, we get this algebraic geometric object. So there is a nice correspondence between those two. So, okay, before that, let me first go into this Montgomery-Young problem. Okay, so we have this circle actions on this r-dimensional sphere, pseudo-free circle actions. And the Seifert is the first one who studied this, and he found that he was actually interested in this three-manifold case. Three-manifold case. And he showed that in this case, the action should be diagonal. Okay. So this kind of thing is the only possibilities. So in particular, in this case, non-free orbits only happens above those vortices. So there are at most 2 non-free orbits. Okay. So the natural question is, what is the bound on these non-free orbits in general? What's the bound of number of non-free orbits? Okay, but a priori we don't know if it is bounded or not. And after that, Montgomery-Young and Petri showed that actually it is unbounded if n is at least 4. So Montgomery and Young first considered the n4 case, and Petri showed that it happens in any higher dimension. Okay, so only the remaining cases when n is 3. We are considering the circle actions on S5. Okay, so this is the Montgomery-Young problem. So it is first appeared in the paper of Finchel and Stern. So the question is, if we consider the pseudo-free circle actions on S5, then it has at most 3 non-free orbits. So this is the Montgomery-Young problem. And actually in this Finchel-Stern's original paper, they claim that they have proved almost all cases. But there was a crucial mistake there. So you can find the crucial mistake on the MathSciNet review. Okay, so the proof is all gone. And it is totally open. It is now, in a sense, completely open. Okay, so in this case, so maybe this is too general. So maybe if we put more assumption, then maybe one can prove the partial cases. So we are going to consider the case when the orbit space has a projective algebraic structure. So this is basically the algebraic Montgomery-Young problem. For that, we need this correspondence more explicitly. So actually, the correspondence was studied in many cases. So Montgomery-Young, when they were doing this, they already considered this kind of correspondences. And then Finchel-Stern and then Polar, like 20s. So there is a bijective correspondence between those circle actions, pseudo-free circle actions, on somewhat slightly more generally Q homology S5 with trivial first homology. Between this object and then algebra geometry, and then 4 manifold. Smooth compact 4 manifolds M with boundary such that we have some conditions. The boundaries are union of length spaces actually. Say Li are length spaces. Maybe spell to AI. Oh, yeah, actually, yeah. So maybe this is one you mentioned. Oh, now I realize. Thank you. Thank you. And then the first homology here is also trivial. And then second homology is Z. Okay. Yeah, so basically if you have this action, then you can consider the OB space, and then OB space is of this form. And moreover, if L is diffeomorphic to S5, here L is only Q homology S5. And this is characterized by claiming that M is simply connected. So there are various versions of this kind of correspondence, and this is the latest one. Okay, and using this correspondence,
So we have this compact four manifold with boundary, and if you put a cone on each of the boundary, which is the length space, then we get this OV-fold structure. And this is natural. And furthermore, if we assume that this OV-fold, four-dimensional OV-fold is projective algebraic, then we have this conjecture. So this is the algebraic Montgomery-Young problem. Okay, and one question here is that, so in general, this four manifold, this four OV-fold did not be projective algebraic. But I don't know any example which is non-algebraic. So I'm really interested in this question. Is it always algebraic or not? So this is also open. Okay, so now we can move to this algebraic geometry. Maybe. Okay, so this is the algebraic Montgomery-Young problem. And actually, projective surfaces with quotient singularities with second batch number 1, this one is called Q homology P2 in the literature. Because in this case, you can easily see that, yeah, second batch number is 1, and you can see that second batch number is 1, so PG is 0. So, and if it has only quotient singularity, then you can also prove that Q is also 0. So this becomes exactly Q homology P2. Okay. If this Q homology P2 has no singular point, if it is smooth, then it is either P2 or what is called the fake projective plane, which is a Ball quotient. And they are completely classified now. There are exactly 100 of isomorphism. But if you allow singular points, then the complete situation is completely different. So in the smooth case, these are either P2 or surfaces of general type. But in the singular case, in general, so S is the singular Q homology P2, then we can take the minimal resolution. Then the Kodaira dimension of this minimal resolution can be arbitrary, actually. So since the second batch number is 1, we have trichotomy for the canonical divisor. So minus k is either ample or numerically trivial, or k is ample. So this case is called Delpejo case, log Delpejo surfaces, log Enriquez surface, or log surfaces of general type. So in this case, the Kodaira dimension of the minimal resolution should be minus infinity. And here we have this bound. So this is kind of trivial bound. And actually there are examples, so they are all occur. So there are examples of each case. So the situation is totally different from the smooth case. Okay, so for those kind of varieties, if we put this more assumption, then we want to show the number of singular points is bounded by 3. So this is the problem. Okay, so in this direction, the first result, no, different, no. Because so for example, in these cases, minimal resolution usually have a lot of -1 curves. So you have this picture, you have this minimal resolution, and then you can have minimal model. In the other case, no. Still we have some non-minimal examples actually. Explicit non-minimal examples. Okay, so so in this direction, so one result is that if S is a Q homology P2, then actually the number of singular points is bounded by 5 without any assumption on the simply connectedness, the smooth locus. But this is actually easy to prove. almost immediately follows from OB-fold version of Bogomolov-Miyaoka-Yau inequality, although we need some more argument. And the main point of this paper was about the characterization of the maximal case. So the 5 case only happens when S prime, the minimal resolution, is actually the minimal Enriquez surfaces. Minimal Enriquez surfaces with and S has singularity of S is precisely 3A1 plus 2A3. Okay. So actually there are one-dimensional moduli of those surfaces, and this is the maximal case. And we want the bound as 3. So we have some gaps to go on. So there are some more studies about this conjecture. So now I'm going to write down what is known about this conjecture. So actually this conjecture is known when the below cases, when S has at least one non-cyclic quotient singularity, then the conjecture is okay. But you might notice that actually this case is not related to the original Montgomery-Young problem, because according to the original Montgomery-Young problem, we only need to care about cyclic quotient singularity. But Kolla somewhat thought that this should hold for any KLT singularity. So he proposed this generality, and Kolla's expectation was correct. And then it is proven that when S is not rational, or K is numerically trivial. So we are only in the rational case, like this. And this case is already gone. So we are left with those 2 cases. And this case is also done. So it is okay when minus K is M4. And the method used is quite different in each cases. So yeah, so in this case we used OB-fold version of Bogomolov-Miyaoka-Yau inequality and lattice theory. So we consider the sublattice generated by these exceptional divisors onto the H2 of this S prime. And if this lattice can be embedded into those ambient lattice and something like that. And here we have proved some kind of intersection theoretic formula that detects some kind of rational curves with given configurations. So it truly relies on this new formula. And in this case, we relied on what is called Mianisch-Zhang's theory, which was developed to classify all local Pell surfaces of Picard number 1. And this is totally different from the others. Okay, so as you see, now the remaining case is this one. So from now on, I'm going to talk about those cases. And it is still open until now. So okay, so it is remains to consider birationally rational Q homology P2 with only cyclic singularities and canonical divisor M. So this is the space that we need to consider. And yeah, and with those additional conditions, we want to show this one. And since this is rational, as you see here, the maximal case only happening when S prime is Enriquez. So if it is rational, we already have the bound 4. So we really want to go from 4 to 3. This is what we want to do. And actually, the first step of this process is to consider orbifold version of Bogomolov-Miyaoka-Yau inequality. So which is of this form. Instead of C2, we need this orbifold C2. And since K is ample, we have this. And this is usual Euler number minus singular point contribution. So this is the local fundamental group around the singularity, and this is the formula. And in this case, the Euler number is 3, and so we want to assume that this surface has 4 singular points and derive a contradiction. So there are 4 singular points. So we have here this way. Okay, and this is -1, so you have -3, and you can move it to there. So move it to there, then this, and okay, this is greater than 0, so we can ignore this. So you can just move 1. So we have this bound. Okay, from this you can easily see that there are several things like this, because these numbers should be co-prime. This is one possibility, and you also have 7 and 11 to 43. So these are the only cases. And Q is not bounded, and the others are all bounded. Actually, in that paper, in the second paper, HK 13, we actually, moreover, we removed this one and this one except for 19, except for 19, yeah. And you see there are 2 types of this. You know, there are 2 different cyclic quotient actions of order 3. And so this is A2 or 1/3, 1, 1. And A2 case is also removed. Okay? This is what is known already. And that was the situation. And recently, this year, also there are many cases for this, but the only remaining case is like this. This is the only remaining one for that. And only this year, maybe in January or February, there were a group of 4-dimensional people. Huh? I will explain it. Sorry for my ugly English, but so they are working on four manifolds. So this is what I mean by 4-dimensional people. So they are people in differential 4 manifolds or simplex 4 manifolds. 3 Koreans, and actually they use this smooth 4 manifold theory to further study these kind of cases. So they have removed. So they removed this case. Okay, they removed this case, and they also show that Q is at least 2,599. So actually, so they cannot do the general thing, but if you fixed the type of singular points, then they can do some kind of smooth surgery to create a new 4 manifold, which is non-algebraic. And then they could prove that these spaces do not exist. So that's how they removed all those cases. So they have used computers to remove all the cases below this order. But at this order, they could find a special type of singularities, which their method doesn't apply. So this is really the current stage of this problem. Okay, so we have used tools from algebraic geometry and tools from smooth manifold, but still the conjecture is open. Okay, so in the remaining time, I want to talk about those spaces rational Q-homology P2 with cyclic singularities with ample canonical divisors. Because these are kind of weird objects. These are rational but general type. So those kind of, so at first I didn't know the existence of such surfaces, but actually Kerr and McKernan already considered those kind of surfaces, but when I was working on, I didn't know the existence of this paper. But Kolla actually gave a different construction. And using this Kolla's construction, I found another way of constructing those surfaces, and using that new idea, I could construct a lot of such surfaces, and actually those are kind of similar to that one. Not sure if I have enough time. So I want to give, yeah. Okay. Anyway, so there are now infinitely many constructions of those surfaces. But the thing is, all known examples have at most 3 singular points. So 1, 2, 3, all possible, but no examples with 4 singular points, without the assumption of the simply connectedness of the smooth locus. So maybe the conjecture is, so S is rational Q homology P2 of general time. Since I'm out of time, I want to write like this. Then maybe without the assumption of simply connectedness, we always have this one. We don't know. And as you see, this is conjecture A implies Montgomery-Young problem. Okay. And maybe I can do some work. So maybe I will give you one example of such. So I need to be very quick, but consider 4 different lines in P2. Okay, and L1, L2, L3, L4. And we have many intersection points, but we precisely choose those 4 points. And we blow up each of those 4 intersection points twice, so that we get this configuration. So maybe it's not very good because I'm lack of time. So you know, L3 with L4, so you blow up this point, then you get this E34. And then you blow up again of this point, so that you get E34 prime. Okay? So this is the notation that I'm using. Similarly, we have this. Yeah, maybe it's not very, yeah, with this short time, maybe you cannot recognize this, but this is correct. So if you block 8 times, then you get this configuration. And here, all those curves are -1 curves, and all the remaining curves are -2 curves. So if you contract all those 8 -2 curves, then you have 2 singular points of type A4. And this is actually perpetual surface. But now the story starts. But if you further blow up this example, this point, really many times, then and then contract, really many times, and then contract, then you have 2 singular points of worse singularity. Or not worse singularity, and at some point you have K ample. So in every such example, using this kind of idea, we have constructed such examples. And this example recovers every known example. So every known example is of this form anyway. So out of this, I want to formulate a conjecture. Okay, so this is about cascade conjecture. Okay, so let S be a rational Q homology P2. And we say that S admits a cascade if we have the following diagram. So we have S and take a minimal resolution. And we do some blow down, smooth blow down. So blow down 1 minus 1 curve. And we get another surface here by contracting the negative curves like this. Under the condition that, okay, here we have pi 0, pi 1, pi t, here phi 1, phi t minus 1. So we want that pi's are all minimal resolutions, and phi is usual blow down, and SI's are Q homology P2. And one more condition is that the final one here, the final one is Delpetzo. Okay? So actually this is coming from my previous example. So in every example with K-ample, they have this kind of blow down to the minimal resolution of a Delpetzo surface. So out of this, so all the known examples have this kind of structure, step by step. So each of these steps is coming from the blow up of the intersection of those kind of curves. Explicitly, there is a correspondence. Okay, since every known example has this structure, so the cascade conjecture is the conjecture that maybe this holds in general. So let S be a rational Q homology P2, then S admits a cascade. Okay, so this is the cascade conjecture. And actually there is another version of cascade. So cascade for log Delpetzo surface is Picard number 1. So this is that every Delpetzo surface of Picard number 1, we have a similar diagram. So that the final one is either Gorenstein or some standard one. So this is, there are finally many such classes, and this is easy to understand. So as a summary, for every rational Q homology P2, we can reduce to the Delpetzo case, and Delpetzo case can be reduced to the Gorenstein case. I mean, AD singularity case or some easiest one. So this is what I have in my mind. So this is done and this is open. And actually I can prove that the main theorem of today is cascade conjecture actually implies conjecture A. Means that even without this simply connectedness assumption, we have this bound. Of course, this implies AMI. Okay, so if you are interested in birational geometry, then to prove this algebraic Montgomery-Young problem, this conjecture is the one that you must solve. Actually, this is really birational geometric because I didn't have enough time to explain the example, but all here has Picard number 1. And actually, you can extract one divisor here, and so you have 2 rays of monochrome, and you can go the other way, then you have this. So you have this kind of Sarkisov program here. But actually, Kill and McConnell also considered the successful program here, but they used all the 4 types of successful links. But here we only need two types of successful links to describe all those surfaces. So this is kind of special. So this is really the problem about successive link for those kind of surfaces. And yeah, I'm really out of time, so that's it. Thank you. So here I'm assuming quotient singularity everywhere. Otherwise, this breaks. Montgomery Young, yes. Yeah, that's right. I see. We don't. Your question is we don't know if the Kobe space is algebraic or not. Okay, I don't know. Maybe yes, but I have no idea. Good question.
So you mentioned at the beginning that the cipher argument for n equals 2
Uh-huh.
and showed that the action is always diagonal, right?
Yes.
Do we know if any example where the action is non-diagonal for
N equals 3, 3 is 5. Yes, there are many actually. There are really many. So, yes. I already erased it, but you know, there are 3 cases like K ample. So the action is diagonal, then we always have this weighted projective plane case. So these are toric, and these are all included in those cases. And all the other cases, the action is non-diagonal.
So we have questions from 2 papers, one student. You kind of related that. Do you have evidence for this?
Evidence is only supported by all the known examples. And that's it. I don't know. Maybe that's not true. I don't know.
The other question comes from the back.
Right. So can I answer a little bit more? Yeah. Sorry, but you know, there is totally another problem that bounding. So Alexeyev and some collaborators were studying the minimum bound of the self-intersection of canonical divisor. And they have a guess for log trapezoid surface of picard number 1. And they have created the one with very small number, like, I don't know, but something like this. They have constructed this example, and we do not know this is minimal or not. And actually, if the cascade conductor is true, then we can also prove this. So maybe this is another evidence. Okay, very good. Yes.
Because somehow this slightly more delicate. About perspective of Lambert, you are working with the surface plus half of the divisor. And then in this case, you can just go with the coefficient.
But do we have a kind of canonical choice for the boundary divisor? Can we have a canonical choice for the boundary divisor in this case? Okay, maybe we can talk about it after the talk.
For the questions, moment. Not, let's thank the speaker.
Thank you very much.